Okay, so the third kind of electrophilic aromatic substitution, say it out loud. Electrophilic aromatic substitution. The first kind of electrophilic aromatic substitution that we're going to do is nitration. We're going to add a nitro group to make nitrobenzene. All right, and as always, the first thing we do is we make a good electrophile, right, from something. Okay. In previous semesters, I've said, hey, let's call this maybe say E star or E something, where the first thing we're doing is we're making a good electrophile. After we've made the good electrophile, the mechanisms all look the same, right? So in order to make a good electrophile, the reagents give a hint about how that works, as always, I suppose. So you have sulfuric acid and nitric acid together, both of them strong acids, so it's a little funny to see nitric acid acting as a base here, but that's exactly what happens. So nitric acid acts as a base, bump, bump, and so you have this mass here, right, which looks like nitric acid, but it's got a proton on it. And what do you have here? You have a good leaving group, right? You see the water? Water leaves, and when the water leaves, we're left with a nitronium ion. All right, so this is linear, and it's got a, wow, look at that, it's linear and it's got an atom right in the middle with a plus charge on it. What? Amazing. Okay, this is a very good electrophile, and that's what we've done then every time, starting out by making a good electrophile. So you know what's going to happen next, right? If you have a piece of paper handy and you've got the spirit for it, you should pause the video and predict what the next picture is going to look like. Okay, so as always, our pi electrons, you're going to have to, I'm working here in a room with my bride, and she's got to make some noise, so hopefully it's not too distracting for you guys. But these pi electrons come and attack the electrophile, right? There we go. And when they do, we get our sp3 hybridized carbon. It's the first time I've mentioned that. Our sp3 hybridized carbon now, right? You see it was sp2. And it goes to sp3. It's got the nitro group on it because that's what this is. Okay, there's our nitro group. And this is going to be resonance stabilized. So that's the first picture of the sigma complex. Pause the video and draw out the sigma complex. Draw all of them out. Okay. Now, there you go. There's the sigma complex. Hopefully that's what you have on your paper. Oh, I hope you're doing that. When I say pause the video, I so hope you're doing that. You're missing out in value. Even if you're getting it wrong, even if you feel lost, maybe you should look it up, but you need to engage your mind when you're doing that. Oh, please, please, please. Okay, so the sigma complex stabilizes the carbocation. Do you know what question I'm going to ask you here? What am I going to ask you about this? Draw the resonance hybrid. That's not a question, I guess. It's a command, right? Draw the resonance hybrid. Now that I've drawn the resonance hybrid, or rather now that I've told you to do that, I'm gonna walk through this with you. Pause the video and do it now, and I'm gonna walk through it with you. Okay, I'm gonna suppose you pause the video. First thing I'm gonna do when I draw a resonance hybrid is I'm gonna draw everything that is common to all of my contributors. Right? You agreed? That's common to all of them. Now I'm going to walk through it. The hydrogen doesn't change in any of them. Hydrogen, hydrogen, hydrogen. And so, there we go. It's a hydrogen, right? All right, let me actually do a different color here for all the things that do change, okay? So, that's a single bond with all of them. That's a single bond. No big deal. This now is a single bond. 1, 2, 3. It's a single bond. Right, so keep that single. This carbon is neutral. Neutral. and positive. So this is going to be partial positive. This bond is double, double, single. So I'm going to make it partial double, right? This is neutral. This carbon is neutral, neutral, and neutral. So this one stays neutral. This bond is double, single, single. So it's going to be partial double, right? This carbon is neutral, positive, neutral. So this is going to be partial positive, right? This bond is single, single, double. Okay. Neutral, neutral, and neutral. So nothing goes on there. Double, double, single. Okay. And then neutral, neutral, and positive. So this is going to be partial positive. Okay. And so that's the sigma complex, and this is the resonance hybrid. Why is this important? Oh, I have not convinced you yet. I know, but I will. In the end of this chapter, I'm going to convince you why this is such a big deal. So again, I encourage you to go through, and you can't get this wrong. If you go through and systematically check every bond, every bond is going to be the average of all the contributors. There's one, here's another one, and there's another one. Those three are going to average up to whatever this bond is right there. Okay? And we do it for every bond and every atom, and you can't get it wrong if you do this systematically and don't miscount. All right, so there's a sigma complex. Now you know what happens next, right? Predict it. Say it out loud. We're going to regain aromaticity, right? So in order to regain aromaticity, we got to take that proton off. Same thing would happen every one of these you've seen, and we've got more, and it's always going to be the same. Proton transfer, going to come there, and this guy's going to come back, bam, and we're going to get our aromaticity back. All right. Now, this is interesting. A nitro group can be reduced to form an amine. So this is, I should have let you say it first. I should have asked you, what is this? It's aniline. And this is nitrobenzene, okay? Let me go back to the beginning of the chapter for a second, okay? I'm going to go back a bunch of slides. There we go. Look at this. Remember this slide? We're going to take benzene and we're going to learn how to make bromobenzene, chlorobenzene, nitrobenzene, benzene sulfonic acid, alkylbenzene, and acylbenzene. But I do not have aniline on here. Do you see what else is missing? What else is missing? Toluene's on here. Where is toluene on here? Well, besides the blue picture I just drew. Where is toluene? Where is... isopropylbenzene? Where is it? It's on here. You see where I'm going with this? Okay. Toluene and isopropylbenzene are all right here. Okay. Phenol is not on here. So I haven't shown you how to make phenol yet. And I'm just now showing you how to make aniline. First of all, in order to make aniline, we've got to make nitrobenzene first. I'm going to go back to the slide where I was. Yep. Make nitrobenzene first. And then we get aniline. Okay, and that's what this is. This is right. You know what I'm doing with you, right? I'm practicing synthesis, which is really high level thinking, and that's why it matters. It also matters that you get a chance to do what a scientist does and build and create. So combining the reactions above gives us a two-step process for installing an amino group to make aniline. Here's our aniline. Okay. So number one, first thing, where's my pen? Did I lose it? Okay. First thing, we're gonna make nitrobenzene with the first step, and aniline with the second step. Okay. Now go and practice with conceptual checkpoint 19.4. Good luck.